Hi, hello, namaste. Today we are going to talk about postulates of quantum mechanics. And we know that whatever we study in quantum mechanics are totally based on this few postulates or set of rules. So we start with it. So we know in classical physics, if I tell you where a particle is located, so where is the particle and how fast is it moving? So basically its speed and somehow its location, then I can actually predict what will happen next. Like, where is it going to land? Is it still going to move? Is it going to pause? I can literally predict its future. So this is what is the speciality of the classical physics. But in quantum mechanics, um, things don't really work like that. So in QM, if you talk about it, it does not work like that, where you have a particle, you have a location. Everything is based on one single thing, or I would say one single word, you can literally say, that is probability. And this is the highlight of quantum mechanics. It's all just, you know, a probability of maybe, maybe not, yes or no. There's no yes or no actually. There is only maybe or maybe not, right? So this is the understanding. So it just gives you the probability. And to describe this new kind of behavior, we use some set of rules, and those set of rules are called postulates. They are the starting rules of the theory, and if we understand this properly, everything else is like much becomes much easier. So we start with the first one, the first postulate. It says that the complete description of a system is given by something called a wave function. A wave function. So wave function is actually represented by something like state, which is equals to psi x comma t. Now you don't worry about the name actually. Just think of psi as like something which actually contains all the information about the system. So at first you might think, okay, so like this is x, this is psi, this is x comma t. So it means that the particle has some position x, so it is at position x with some time t, right? But that's really not true. So what I can say is that like psi x comma t is not equals to some position. Okay, it is not equals to some position. So what do we actually, like, what does this actually does? That should be the question. So what is psi? So let's think, can psi itself be the probability? Like, you literally started with the word probability here. Can psi itself be the probability? Well, no, it cannot. So psi can be complex, and something which is complex, it has imaginary parts. But we know that probability, and I think you should think of probability as a form of nature. So if I call probability a nature, then nature should always be real and positive. But then we get to know that psi can be complex and it has an imaginary part. So how does it fit? How does it fit the our idea of psi or its meaning? So we need basically a way to turn psi into something real and meaningful. So what do? We do that by taking modulus with squared. So squared modulus. So we can literally write it as psi square is equals to psi star psi, and this gives us real as well as positive quantity. And this is what we interpret as probability density. This is what you call as probability density. So when we started with it, we wrote psi x comma t, and we thought, yeah, this might be the one which is giving position with time. But then no. So psi itself is not directly measurable. It is not measurable. But psi square, it tells us the particle and where it is like likely to be found. So quantum mechanics does not tells us the exact position. So of course, but it can tell us where the particle is likely to be. And also this wave function must satisfy few conditions. If I have talked about wave function x comma t x square psi square, then it has to fit into some conditions. The first is normalization, or it should be normalized. The second is the continuous, which is basically the nature of this wave function. And third is the single valued, which talks about its uniqueness. Now from this understanding we can move to postulate second. What does it say? I can call this something as observables as operators. What does this mean? So once we have psi, we have psi now, we understood what psi is, we have a little idea of psi. The next question is, and we also talked about that, how it contains all the information about the particle or the system or the wave function. Then the next question is, how do we find things like position, how do we find momentum or energy, how do we find them? So in classical mechanics, what exactly it is. So in classical mechanics, what do you usually do? You have something like, this person is walking 5 kilometers per hour. So everything is in numbers. 5 kilometer per hour, the energy is this much of energy. So everything is based on something as numbers, which is not same, or we don't get directly numbers in quantum mechanics. So instead we use something called as operators. An operator is just a rule. It takes a function and gives another function. So how do we understand this? When I said it is just a rule, it takes one function and gives another function. So d by dx, is basically an operator, and if it acts with something, let's say example x square, so it gives out 2x. So like I said, an operator is just a rule. It takes a function and gives another function. So in quantum mechanics, every observable has its own operators. Every observable has its own operators. For example, you have x, which can be written as x. You have p, which is basically your momentum. Momentum is of course different here, so it is written as I h cut d by dx. So instead of like plugging values, like we usually do, we apply operators to the wave function psi. Now here's the important point which we should actually think about is when we measure something, the result must always be real. Like I said before, real and positive is something which we always expect from our result. So if we choose operators carefully, so like of course if we choose it carefully, then they will always give us real values, right? And this special operators, they are basically called as, and you might have heard about it, Hermitian operators. And this basically gives us real values. So you don't need to worry about the full definition right now, but just remember this ensures that whatever we measure actually makes physically sense. Now we move to the third postulate. Postulate third. So now we come to the most interesting part about the measurements. So of course in classical physics, if you measure something, you simply read its value, right? But in quantum mechanics, measurements, it works very differently. Before you measure, the system does not have a single definite value. So instead it exists in, like, I can say combinations, and many possible combinations, by the way, many possible combinations. So it can be something written like psi is equals to cn psi n, oh sorry, phi n. This is one of the combination. So you can think of it like this. So this particle is like, it's not at one place, but at multiple possibilities. So how do you understand this so let's say you have a chamber, you have a box. So the particle can be anywhere. It can be here, it can be here. So this is what you're talking about, multiple possibilities of a particle to be in one state or multiple state. So each possibility has a certain chance of appearing. The particle can maybe appear here, or it can appear just here, or maybe somewhere at the top of the corner or this corner. That is what we are talking about. So like I said, each possibility has a certain chance of appearing. Each possibility has a certain chance of appearing, and basically this chance is what you call is again probability. See the significance of the word probability in quantum mechanics. And of course you can write this as this, which you just did here, multiple possibilities. You can write it as like this, as cn square, modulus of cn square. So before measurement we always have probabilities, not a definite answer. But the moment we measure, right, the moment we try to measure it, we get a specific result. We do get a specific result, and after that the system, it stays in that state. The system stays in that state. And this is where we say, a very famous term, where we say the wave function collapses. So how does it collapse? So like I said, you have multiple possibilities of where a particle is likely to be. You choose one point. Oh, this is where the possibility is where this particle is. So what happens? The whole of the wave function, which you assumed this might be, now it turns out to be just this little one particular state, and that is where you say that the wave function collapses. So it collapses to one state. So measurement actually does not reveal the system; it actually changes the system, right? So technically, if like what we measure are the sorry eigenvalues of the operator. But for now, like, you can just remember it like this, like, if I can simplify it. So we can, like we say, before measurement you have many possibilities, but after the measurement you have one definite result. Okay, so this are the first initial postulates. Now we move to the next postulate, which is postulate 4, which basically deals with time evolution. Postulate 4. So the next question, as we move, right? If you know the wave function right now, how does it change with time? So if I know a wave function, how does it changes with time, or you say evolve with time? So of course, in classical mechanics, again in classical physics, we use equations like Newton's law to predict motion. But in quantum mechanics, we use the very famous Schrodinger's equation. Schrodinger's equation, and of course, it is written by I h cut dou psi by dou t is equals to h psi. So this equation tells us about the wave function and how it evolves with time. So if you know what psi is at one moment, so let's say you know about psi somewhere at one moment, so this equation tells you psi at any future time. That is the speciality of this equation. So of course, the thing is, this part is deterministic. That, when I started talking about classical physics, how actually you can predict the future. So you might think, okay, so does this mean you can predict future in this sense? Yes, this part is deterministic. This part is deterministic, but not all of it. That doesn't mean that the whole wave function, evolves smoothly deterministic, like I said. So of course, the measurement is still probabilistic. Measurement is still probabilistic. So in quantum mechanics, so you have both the ideas together. Now the next is postulate fifth. So we talk about what we actually observe in experiments. If you repeat the same experiment multiple times, so, for example, you have, let's say, this state, this state, this state, this state, and multiple states like this. You repeat the experiment. Let's say you have a particle, it is just moving inside. You repeat this experiment multiple times, over and over and over again, right? So you get an average. You get an average value, right? And this average value is something called as expectation value. This is called as expectation value, and you can actually write it as the integration psi star a psi dx, and this formula actually gives you the average result of any measurement. So even though individually results are random, if you take the average, then you can say it is predictable. It has a pattern, which you can literally predict. And like, this is how you connect quantum mechanics to classical physics. And then we come to the final postulate, which is postulate 6, which is normalization. Like we discussed earlier. So now this is actually one of the most important ideas. Since psi square, it gives you probability. The total probability must be equal to 1. That is the rule. That means the particle must exist somewhere at the end. It must exist. The particle must exist somewhere. And this is how you can represent it as psi x comma t with integration square dx is equals to 1. This is called as my normalization. If it is not satisfied, I'm really sorry, if it is not satisfied, this condition not satisfied, then wave function is not physically valid. So with this all 6 postulates which we just now discovered, let's just come to the conclusion and conclude everything what we just now learned. So state, what is a state? It's a psi. Probability, it's psi square. My observable is basically my operator, and my measurement is given by my eigenvalues. And time evolution, we just discovered that time evolution is basically my Schrodinger's equation, and expectation is my average value. And then you have normalization, which is basically equals to 1, which is my total probability. I hope you were able to understand it. Thank you so much for watching.